Hello one and all, this is Rajesh of CIC. Now I'm going to give a seminar on wave optics. Coming to the introduction of wave. Firstly, what is a wave? It is the disturbance in which energy is transferred from one place to another place. It travels through space, matter. Wave motion transfers energy from one point to another. As we all know, there are two types of waves. One is transverse wave and another one is longitudinal wave. This is an example of surface waves produced in water. Now coming to transverse wave. What is a transverse wave? In physics, a transverse wave is a wave whose oscillations are perpendicular to the direction of wave's motion. The highest point in a transverse wave is crest and the lowest point in transverse wave is trough, as you can see in the diagram. Now in a wave there are wavelength and amplitude, medium. Now what is the wavelength? Wavelength is the distance between identical points like adjacent crests or adjacent troughs in the cycle of a waveform. Now coming to the amplitude. What is an amplitude? The amplitude of a wave is the distance from the center line to the top of a crest or to the bottom of a trough. Now coming to the medium or matter. The matter through which the wave travels is called medium. This is the motion of transverse wave, as you can see in this video, where the oscillations are perpendicular to the direction of wave's motion. Now coming to longitudinal waves. Longitudinal waves are the waves where the vibration of medium is parallel to the direction of wave and the displacement of medium is in the same or opposite direction of wave propagation. Here in longitudinal waves, the displacement of medium is parallel to the wave, right? Now as you can see in the diagram, here we are having compression and refractions, right? Now what is meant by compression? Compression is a region where the particles are closest together. And what is meant by refraction? Refraction is the opposite of compression. It means where refraction is a region in longitudinal wave where the particles are far apart. This is the motion of longitudinal waves, as you can see in the video. Here the displacement of medium is parallel to the propagation of wave. Now coming to optics. What is meant by optics? Optics is a branch of physics that studies the behavior and properties of light. Here, optics usually describes the behavior of visible, UV, and infrared light. And this phenomena depends on the fact that light has both wave-like and particle-like properties. Explanation of these effects require quantum mechanics, and quantum optics deals with the application of quantum mechanics to optical systems. Now coming to the applications of optics in daily life. Optical science is relevant to and studied in many related disciplines including astronomy, various engineering fields, photography, and medicine. Now practical applications of optics are found in a variety of technologies like including mirrors, lenses, telescopes, microscopes, lasers, and fiber optics, etc. Coherency. What's meant by coherency? Coherence, a fixed relation between phase of waves in a beam of radiation of a single frequency. Two beams of light are coherent when the phase difference between their waves is constant. When there is a random change or the phase is different, then those two waves are called non-coherent. In physics, two wave sources are coherent if their frequency and waveform are identical, and they are called coherent sources. Now, what is meant by phase and frequency? Phase. The phase is defined as the position of a point in time on a cycle of a waveform. Now, what is meant by frequency? The number of occurrences of a repeating event per unit time is called as a frequency. These are some examples of coherency. In the first diagram, and in the first one is LED and the second one is laser. As you can see in the LED, the phase differs from one wave to another wave, so that is non-coherent, right? Now coming to laser, and see here the phase is same for the three waves, so they are called coherent. Yeah, okay. Now in the second diagram, the fourth one is coherent, right? And the first, second, and third are non-coherent because the phase differs from one wave to another, right? These are the examples of coherency. Now coming to the superposition principle. The superposition principle states that for all linear systems, the net response caused by two or more stimuli is the sum of the responses that would have been caused by each stimuli individually. So for example, if input A produces response X and input B produces response Y, then the input A plus B produces response X plus Y. When two or more waves meet, they interfere and produces a resultant wave whose properties can be calculated by using the principle of preposition. According to this wave, when two or more waves traveling through medium, when they superimpose one another, a new wave is formed, in which the resultant displacement at any instant is equal to the vector sum of the displacements due to individual vectors at that instant. So, if you consider this diagram, wave 1 represents y1, wave 2 represents y2, and the resultant is formed when wave 1 is superimposed with wave 2. So by the superposition principle we can say that y is equal to the vector sum of y1 plus y2. Now coming to the interference. What happens when two waves meet each other like we do while they travel through same medium? It's simple, interference takes place. In physics, interference is a phenomenon in which two waves superpose to form a resultant wave of greater, lower, or the same amplitude. Constructive and destructive interference results from the interaction of waves that are coherent with each other either because of they're from the same source or because they're having the same frequency. Here, interference can be observed in all types of waves like light, radio, surface water waves, gravity waves, or matter waves, etc. Now coming to the example of interference. We all know that interference is of two types. One is constructive and another one is destructive. These are the examples of constructive and destructive interference. And the left one is constructive because it is in phase. So the two lower waves create constructive interference. And the right one is 180 degrees out of phase, right? So they create destructive interference. Now coming to constructive interference. Constructive interference, where two waves of same wavelength interact in such a way that they align, leading to a new wave that is bigger than the original wave. And the maxima is equal to the addition of two waves. And the amplitude is equal to the sum of individual amplitudes. As you can see in the diagram, the first wave and the second wave interact and they give a bigger wave, that is the third wave. This is the example of constructive interference. Now coming to destructive interference, where when the maxima of two waves are 180 degrees out of phase, a positive displacement of one wave is cancelled exactly by a negative displacement of another wave. The resultant amplitude is equal to 0. It is 0 every time in destructive interference, as you can see in the diagram. They are 180 degrees out of phase, so the positive is cancelled by the negative, and it forms a destructive interference where the resultant amplitude is equal to 0. This is the example of destructive interference. Now coming to Young double slit experiment. In modern physics, the double slit experiment is a demonstration that light and matter can display both waves and particle nature. In this experiment, a wave is split into two separate waves, then later combined into a single wave. This leads to a phase shift, creating an interference pattern. As you can see in the first diagram, light is passed through double slit, and on the screen you can observe interference patterns, right? And on the right side, this is the constructive interference, and the second one is destructive interference. As you can see in the left diagram, light is passed through single slit and next double slit. Here phase shift occurs and interference takes place, and bright and dark bands are formed on the screen, as you can see in the diagram. And in the right side, this is the dark. That means destructive interference is called as dark band and the constructive interference is called as bright band, as you can see in the diagram. Now coming to path difference. D sin theta is equal to m lambda is the formula for constructive interference. For m is equal to 0, 1, minus 1, 2, minus 2, etc. Now coming to d sin theta is equal to m plus 1 by 2 into lambda is the formula for destructive interference. where m is equal to 0, 1, minus 1, 2, minus 2, etc. As you can see in the diagram, d is the distance between the slits, theta is the angle related to the incident direction of wave, and m is the order of interference. Thin film interference. Thin film interference is a natural phenomenon in which light waves are reflected back by the upper and lower boundaries of a thin film. In optics, a thin film is a layer of material with thickness that is equal to sub-nanometer to micron range. As light strikes the surface of film, it is either transmitted or reflected at the upper surface. Light that is transmitted reaches the bottom surface and may once again be transmitted or reflected. Right, this is the thin film interference. Now coming to the thin film interference experiment, as you can see in the diagram, PQ represents top layer of thin film, RS represents bottom layer of thin film, T represents the thickness of thin film, R is the rarer medium, mu1 is equal to refractive index of air medium, mu2 is equal to refractive index of denser medium, D is equal to denser medium, R is refracted angle, I is incident angle, CD is equal to the refracted ray of bottom, AB is the incident ray, R1 is the reflected ray, BC is the refracted ray, and the sigma is equal to the path difference. Path difference in parallel thin films. Path difference BC plus CD in film minus Bn in air. We know that a distance in air is numerically equal to mu times the distance in medium. Path difference is equal to mu times BC plus CD minus Bn. From the figure, it is clear that BC is equal to CD. So path difference is 2 into mu into BC minus Bn. In the triangle BND, sin I is equal to Bn by BD. We all know the formula, sin I is equal to opposite side by hypotenuse, right? So I sent BD that side. So Bn is equal to BD into sin I. I replaced sin I by mu into sin R. From Snell's law, we know that refractive index is equal to sin I by sin R, right? So Bn is equal to mu into BD into sin R. In the triangle BCM, sin R is equal to Bm by BC. We know that Bm is half of the BD. So I replace Bm by half BD. Then sin R becomes half BD by BC. I sent half and BC that side. Then BD is equal to 2 into BC into sin R. Now I substitute this in the path difference formula. Then Bn is equal to mu into 2 into BC into sin square R. Now this Bn I substitute in path difference formula. So path difference is equal to 2 into mu into BC minus 2 into mu into BC sin square R. Now I take the common terms apart, that is 2 into mu into BC. And when we take common terms apart, path difference becomes 2 into mu into BC into 1 minus sin square R. We all know that 1 minus sin square R is equal to cos square R, right? So the path difference is equal to 2 into mu into BC cos square R. Here the missing term is BC, so we should find that. Now in the triangle BCM, cos R is equal to Cm by BC, where Cm is the thickness, right? So cos R is equal to T by BC. If I send that BC that side, BC into cos R is equal to T. See, that is the missing term, right? If I replace BC into cos R by T, then the path difference becomes 2 into mu into T into cos R. So the formula for path difference is 2 into mu into T into cos R. Now the condition for constructive interference and destructive interference. Here the path difference should be equal to n lambda, where the path difference is 2 into mu into T into cos R minus lambda by 2. That should be equal to n lambda. So if we send lambda by 2 that side, and 2 mu T cos R is equal to 2n plus 1 by 2 into lambda. Here this case is bright. In this case we get bright images. When n is equal to 0, 2 mu T cos R is equal to lambda by 2. When n is equal to 1, 2 mu T cos R is equal to 3 lambda by 2. When n is equal to 2, 2 mu T cos R is equal to 5 lambda by 2. These are the conditions for constructive interference. Now coming to destructive interference, path difference should be equal to 2n minus 1 into lambda by 2, where the path difference is 2 into mu into T into cos R minus lambda by 2. That should be equal to 2 minus 1 into lambda by 2. So if we equal them, when we send lambda by 2 that side, it gets cancelled, and 2 into mu into t cos r is equal to n lambda. Here we get dark images. When n is equal to 0, 2 mu t cos r becomes 0, and when n is equal to 1, 2 mu t cos r becomes lambda, and when n is equal to 2, 2 mu t cos r becomes 2 lambda. These are the conditions for constructive interference and destructive interference. These are some examples of thin film. See, as you can see in the diagram, the soap film demonstrated by the Harvard University is on the right side, and the third picture is a color for interference pattern is observed when light is reflected from the top and bottom boundaries of a thin oil film. These are the examples of thin film. These are some more examples of thin film. Colors in light reflected from a soap bubble, and the right side is thin film interference in a soap bubble where the colors varies with the film thickness. So when there is a change in thickness, the colors also change, right? Experiment done by Harvard University. These are the thin films observed by Harvard on soap bubble. These 5 pictures represent the thin films observed by the Harvard on soap bubble. Okay, right? These are the examples of thin film in real life. See, on the right side, that's an oil film. I have seen that so many times in my life. And on the left side, that's a soap bubble thin film interference. These are some examples in real life. Now coming to Newton rings. Newton rings is a phenomenon in which an interference pattern is created by the reflection of light between two surfaces, a spherical surface and an adjacent touching flat surface. It is named after Isaac Newton, who investigated the effect in 1666. When viewed with monochromatic light, Newton rings appear as a series of concentric, alternating bright and dark rings centered at a point of contact between the two surfaces. When it is viewed with white light, it forms a concentric ring pattern of rainbow colors because of the different wavelengths of light interference at different thicknesses of air layer between the surfaces. So as you can see in the diagram, this is the Newton rings observed through a microscope. Okay. Coming to Newton rings experiment, here we have a source, lens, traveling microscope, plain glass plate, and plano-convex lens and circular glass plate. These are the apparatus required for Newton rings experiment. We can derive path difference, wavelength, number of images of interference, thickness, refractive index, and refractive angle using these Newton rings. Now coming to the path difference, in Newton rings, path difference is equal to 2 mu t cos r plus lambda by 2. Here mu becomes 1 because it is an air medium, and r is equal to 0, and theta becomes 0, so cos 0 is equal to 1. Then the formula becomes path difference is equal to 2t plus lambda by 2. So there will be two conditions. One is brightness and second one is darkness. For brightness, path difference should be equal to n lambda. So when I send lambda by 2 right side, then 2t is equal to 2n minus 1 into lambda by 2, where n is equal to 1, 2, 3. Here lambda is the wavelength of light used. This is the condition for brightness. Now coming to darkness, path difference should be equal to 2n plus 1 into lambda by 2. So if I send lambda by 2 right side, then plus lambda by 2 and minus lambda by 2 get cancelled, and 2t is equal to n lambda, where n is equal to 1, 2, 3. This is the condition for darkness. Now coming to the determination of wavelength, that is represented by lambda. Lambda is equal to 4 mu t cos r divided by 2n plus 1. This is for bright image. Now coming to dark image, lambda is equal to 2 mu t cos r divided by n. Now coming to the determination of images of interference, that is represented by n. N is equal to 4 mu t cos r minus 1 divided by 2 lambda. This is for bright image. Now coming to dark image, n is equal to 2 mu t cos r divided by lambda. Now coming to the determination of thickness, that is represented by t. T is equal to 2n plus 1 into lambda by 2 whole divided by 4 mu cos r. This is the formula for bright image. Now coming to the dark image, t is equal to n lambda divided by 2 mu cos r. Now coming to the determination of refractive index. For bright image, refractive index is equal to 2n plus 1 into lambda divided by 4t cos r. For dark image, refractive index is equal to n lambda divided by 2t cos r. Now determination of refractive angle. For bright image, refractive angle r is equal to cos inverse of 2n plus 1 lambda divided by 4 mu t. Now coming to dark image, refractive angle r is equal to cos inverse and lambda divided by 2 mu t. To the expression for radius of nth dark ring. As you can see in the diagram, it is the radius of Newton's ring, and here SA is equal to AP is equal to nth radius, and OA is equal to T, and AN is equal to 2R minus T. By using the formula SA into R, AP is equal to OA into AN, we are going to derive the expression for radius. So if I substitute all the terms, then the expression becomes R square N is equal to T into 2R minus T. Here we are neglecting T square because comparing with 2R, it is so small, so we are neglecting it. So R square N becomes 2RT. If I send R to the left side, 2T is equal to R square N by capital R. According to the condition for darkness, it should become, or it should be equal to n lambda. So 2T is equal to n lambda. So R square N is by capital R should be equal to n lambda. So if I send R to right side, R square N is equal to n R lambda, and if I send square that side, it becomes square root. So Rn is equal to square root of n R lambda. This is the expression for radius of nth dark ring. Now coming to the constructive interference and destructive interference conditions. So firstly, constructive interference. 2 mu t cos r is equal to n lambda for bright interference. So here path difference should be equal to n lambda, right? So path difference, formula is dn square divided by 4r plus lambda by 2 should be equal to n lambda. Why I sent lambda by 2 to right side, then d square n divided by 4r is equal to n lambda minus lambda by 2, and d square n by divided by 4r is equal to 2n minus 1 into lambda divided by 2. Then I sent 4r to right side, then d square n is equal to 2n minus 1 into lambda by 2 into 4r. Then I sent square that side, it becomes square root. So the dn is equal to square root of lambda into 2n minus 1 into 2r. Here dn is the diameter, which is equal to 2r. Okay, now coming to the destructive interference. 2 mu t cos r is equal to 2n plus 1 into lambda by 2. That is for dark interference, or sorry, dark band, that is destructive interference. Here path difference should be equal to 2n minus 1 into lambda by 2. Here then path difference is dn square divided by 4r plus lambda by 2, which should be equal to 2n minus 1 into lambda by 2. So I sent lambda by 2 that side, right side, then it becomes minus, then dn square divided by 4r is equal to n lambda minus 2 lambda divided by 2. Here 2 gets cancelled, and d square n divided by 4r is equal to n minus 1 into lambda. I sent 4r to right side, then dn square is equal to n minus 1 into lambda into 4r, and then I sent square that side, it becomes square root, right? So dn is equal to square root of lambda and 4r. Here we didn't consider n minus 1, we interchanged n minus 1 with n because there is no concept for negative images, right? If n is equal to 0, that becomes minus 1, right? There is no concept for negative images, so we took n instead of n minus 1. So dn is equal to square root of lambda and 4r. These are the conditions for constructive interference and destructive interference. Now coming to the applications of Newton rings. There are a lot of applications, like we can determine the wavelength of monochromatic light, we can determine the refractive index of liquid. Here is how we determine the wavelength of monochromatic light using Newton rings. We all know that d square n is equal to n lambda 4r, right? I derived that before. So I replace n with n plus m. So d square of n plus m is equal to n plus m into lambda into 4r, right? So I subtracted the second equation with the first equation. So d square n plus m minus d square n is equal to n plus m into lambda into 4r minus n lambda 4r. Here n lambda 4r and minus n lambda 4r gets cancelled, and d square n plus m minus d square n is equal to m lambda 4r. So lambda is equal to d square n plus m minus d square n divided by m 4r. Thus we can find the wavelength of light using Newton rings, right? This is amazing. These are the apparatus required for Newton rings. As you can see in the diagram, this is the apparatus required for Newton rings. Okay. Thank you for giving such a wonderful opportunity. And this is Rajesh of CIC signing off. Thank you.